Hello everybody, my name is Saborno Isaac Berry from Berry Science Lab, and today we'll be looking at a little bit of irrationality and the zeta function. So, an irrational number at its base is any number alpha that is not in the set of rational numbers. In other words, that means that alpha cannot be expressed as P over Q.
What are we doing actually? I totally forgot.
Just irrationality. So it will not be equal to P over Q given the greatest common divisor of P and Q is equal to 1. So, or I guess you could call it greatest common factor. So, this is essentially what we're dealing with here. An irrational number is just something that cannot be expressed as a ratio of two co-prime integers. But we need a little bit of a deeper definition than this. Why? Because it suffices for some numbers, like let's say the square root of 2, it's actually best to prove using this method. You use a proof by contradiction. So root 2 is equal to P over Q. P and Q are co-prime. So then square both sides. Multiply both sides by Q squared. Suddenly you recognize that P squared is even because it's divisible by 2. If P squared is even, that means that P is even. So if P is even, P squared is divisible by 4 because P can be written as some integer multiplied by the number 2. So P squared can be written as that integer squared multiplied by the number 4, which means this is divisible by 4, which additionally implies that if we divide both sides by 2, since this is divisible by 2, this has to also be divisible by 2, suggesting Q squared is even. So Q is even. But that means that P and Q are both divisible by 2, which means their greatest common factor is actually 2, but that's a contradiction to the problem statement, which means that we have a beautiful proof by contradiction. But that's not how every single one works. For instance, what do you do with pi?
Can you now use different color? Mixing up.
It doesn't look good. What do we do with pi? I mean, pi is a transcendental.
Can you then do it on the other side of the board?
Pi is a transcendental number. So there's not really any algebraic manipulations that you can use to work with it. You can't square it, that makes things worse. I mean, you can't divide it by 2 or anything. There's nothing you can do to get at it. It's not similar to something like the golden ratio, for example. So, for these kinds of numbers, what do we do? Well, let's look back at the square root of 2. Let's see how well we can approximate this using a rational number. So, what I'm going to do is I'm going to take P over Q, I'm going to let Q be 1, and then 2, and then 3, and so on and so forth, and I'm going to choose P so that it's going to be as close to the square root of 2 as possible. And of course, I have a calculator right here to assist me with that. So, let's try it with 1, 2, 3, 4, 5, 6, and 7. Let's see how this does. So the square root of 2, looking at dividing by 1, you have two options. You can pick 1 or you can pick 2. This is 0.41 away, but this is 0.59 away, which means we of course pick 1 divided by 1. The closest we can get with this is 1.5. The closest we can get with this is, I believe, 4/3, or 1.33. Or is 5/3 closer? No, that's definitely farther. When dividing by 4, we do essentially the same thing as we did when dividing by 2. 5/4 brings us less close than 6/4. Now, when we're dividing by 5, we can do 7/5, which is about 1.4. When we're dividing by 6, we could go 8/6, but that gives us 1.33. And 9/6 is a little bit closer, which once again follows this pattern. And when we're dividing by 7, I believe 8/7 is no, 9/7, no, 10/7.
Isaac, don't block it.
Yes. So, let's look at everything overall and see what the differences between each one and root 2 are. So, the difference between 1/1 and root 2 is about 0.412. Pretty simple. The difference between 3/2 and the square root of 2 is 0.086. The difference between 4/3 and the square root of 2 is 0.081. And this is going to be the exact same, 0.086. This is going to be 0.012. This is going to be the same thing, 0.086. This is going to be 10/7, 0.014. So as you can see, there's a sharply decreasing trend. And as you go further, I've actually ran the code on this. You will notice...
Using what language?
Python. You will notice that the accuracy of these approximations, or rather their error, looks a little something like this.
Y/x, 1/x?
1/x squared. And so, this right here, that too is called the degree of irrationality. And in fact, that arises from the square root of 2 being a solution to a degree 2 polynomial. So, 1x squared minus 2 is equal to 0. It's a solution to this second degree polynomial. And I know what you're thinking. Rational numbers are solutions to first degree polynomials. Are roots of first degree polynomials. And yes, that does mean that if we're trying to approximate a rational number, it's actually going to be slower than an irrational number, which is quite fascinating. So that's going to be 1/x. And then, of course, we have the very interesting ones. Because being within this range, being anywhere lower than 1/x, or, as this increases, eventually 1 divided by x to the n appears to resemble a 90-degree angle, sort of. But there were a few special functions.
90 degree, oh my god. Did you expect that?
Yes. The slope from 0 to 1 approaches negative infinity, and the slope from 1 to infinity approaches 0.
Oh, okay, got it.
But here's the thing now. There are some functions that decline even faster than any inverse exponential. Well, it's not an inverse exponential, but any function of the form 1/x to the n. For instance, 1/x factorial. And that's actually the approximation rate of a very special number, one of the most famous Liouville numbers, which is 0.1. It's 0.110001.
How do you remember this? How many zero? Is it
4?
Is it opposite to the Google flags?
No, it's an irrational number, of course. But here's what.
You memorize this?
This is equal to the sum of 10 to the minus n factorial, or 1 over 10 to the n factorial, which means that this is 1 factorial, because this is the first digit. This is 2 factorial, the second digit. This is 3 factorial, the third digit. This is the 4 factorial, the 24th digit. Well, this is actually the 6th digit. And this is the 24th digit. And I guess, as you can expect, the 5th one is all the way at place 120. And so, you'll notice that, already 0.11 is an incredibly good approximation of this. It declines, well, the error declines at a rate of c divided by x factorial. And if you study number theory or graphs a lot, you'll know that x factorial grows faster than any exponential function, no matter how big n is. At some point, it will be overtaken. And the reason for that is, think about x to the 100, for example. Now, x to the 100 is pretty big. 100 to the 100 is a lot bigger than 100 factorial. But is 200 to the 100 bigger than 200 factorial? No. Why? Think about it. Here we have 100 terms that are being multiplied. Here we have 200 terms that are being multiplied. It's really just that simple. So essentially, all that we're saying here is that this function is so well approximated that it's not a root to any algebraic function. And so, that's exactly how we know that such a thing is transcendental. If something is not a root of a polynomial with integer coefficients, then it's transcendental. And for example, this is a transcendental number right here.
So can we say that this is a proof of transcendental number?
Yes, this was actually how Liouville proved that transcendental numbers existed all the way back in 1858.